Recording is rolling. It is Tuesday, October 4th. So we're going to wrap up this dynamics unit, forces, masses, forces on mass cause acceleration. Kind of where we started. You guys might remember we started this whole topic with this 10, these 10 mini labs. You guys remember this? And you need the spring scale to do those 10 mini labs. And I told you guys about the operation spring scale, something called Hooke's law. So we'll do an activity on that. Then we're going to flip over and do some conceptual questions with Kahoot, right, to wrap up this topic. I just gave you guys a forces quiz before I started this recording. So double check. Does anybody not have this page? Everybody got this page, right? You guys got this? All right. So that is due this Friday. Now, you guys know this Friday is the end of the first quarter, right? So I really do need these quizzes in by then. You know, it might not be a bad idea to turn this in early. If you finish this by tomorrow, you can pop this in grade trade tomorrow. Have that off your hands. Okay. You guys know also by Friday I'm picking up this page. You guys remember chapter 1 or chapter 4, chapter 5, course in 1 dimension, 2 dimensions. Okay. Now the problems I assigned, I already covered these in class. So as long as you've been following along, then you guys got the answers, right? Okay. So if you haven't turned this in already, some of you guys may have turned this in early, right? Then also turn this in by Friday, right? Of course, the quiz is open notes take home. So if you want to hold on to the problems while you're doing the quiz, might help you out. All right, who has any questions about the setup? You guys good so far? All right, so let's set this spring scale activity. So I have a spring scale here. The spring scale is brown, but around on the desk there are green spring scales, blue spring scales, gold spring scales. There's white ones, red ones. Okay? And each color spring scale has a different stiffness spring in it. Okay, I wonder how stiff the spring is exactly. Could I quantify that? And again, that's actually where we started this whole topic back a couple weeks ago. Okay. So you guys remember this is something called Hooke's. Yeah, thank you. Law. Okay, so Hooke's law, and this is a poster that's hanging on the ceiling above me somewhere. Okay, so suppose you have a spring. There's a spring right there, right? It's got no forces on it, so it's not stretched or compressed. It's just hanging out, right? And now I'm going to put a force on it. Actually, I'll put a couple of forces. Let's do equal and opposite forces. I'm going to stretch the spring out. So there's a force there. There's an equal and opposite force there. You guys remember Newton's third law of motion says forces always come in pairs like this, right? Right? Equal and opposite forces. There's a pair of equal and opposite forces. Right. Here, guys, fall up here. I'm gonna have you guys figure something out. Okay. So a little bit of review here, and how much it stretches x. So that x, how much it stretches. Yeah, that depends on how much force I put on it. If I triple the force, then it should triple the stretch amount. Okay. It also depends how stiff is the spring. And if you quantify that with spring stiffness, spring constant called K, right? And do you guys remember what's the formula that ties these three variables together? F equals KX. You guys remember that? Right. Some textbooks say negative KX, throw a negative sign there. It depends which force you're talking about, right? Which one of these. Right? Anyway, that's that. F equals KX. So I see a direct relationship between the force and the stretch amount, right? Now, what if the question is, what is the spring constant? What is the spring constant right here? Right? Hey, if I know how much I stretch it, X, and how much force that required, F, could I solve for K? Heck, let's solve in terms of variables. Thank you. Let's solve in terms of variables. All right. So could you guys solve for K in terms of variables? It would look like that, wouldn't it? It would look like that. Right? Is that okay? Right. You guys see that matter, the same idea, just rearranged a little bit, right? Okay. Now, here. Let's do the brown scale as a demo, but then you guys got different colored scales. I'm going to ask you guys some of the other ones here in a minute. Okay. Suppose I max out the scale, which is like 10 newtons. There's 10 newtons right there. Right now I'm applying a 10 newton force. Actually, a pair of forces, right? 10 newtons, I'm pulling either way. Okay. So K spring constant equals a force on the stretch amount. So if I plug in 10 newtons right there, right, and it stretches, how much does that stretch? Well, break out a ruler. How much is it from 0 to 10 newtons? That is 5.2 centimeters. Looking at 5.2 centimeters. So I'll put in 5.2 centimeters. What is that? What is 10 on 5.2? That is 1.92 newtons per centimeter, right? Because you guys remember all numbers have attached units in this class. There's a couple exceptions, but this is not one of those exceptions. So newtons per centimeter, right? But a more standard way to represent spring constant is in newtons per meter. So hey, do you think you could convert that to newtons per meter? How would you do that? 1.92 newtons per centimeter. Guys, how many newtons per meter is that equal to? You guys remember dimensional analysis? Railroad tracks? You guys remember that? Right? How many centimeters in a meter? 100, right? How many cents in a dollar? 100, right? Are there 100 centimeters per 1 meter? Is that true? Right? Ah, 192 newtons per meter. There you go. That right there. Actually, these are both valid ways to express the spring constant in this spring scale. Like how stiff is the spring? 192 newton per meter. Okay. Suppose I had a really long spring. I know this is real short. It's only like a few centimeters long. Well, what if I had a really long one, like half the width of this room? Okay. And it was equally as stiff. So suppose I was blindfolded and I started pulling on it. It felt like an equal pulling force for an equal change in length. Right. So if I was blindfolded, I couldn't tell the difference between this one and a really long one, right? So, okay. And I put 192 newtons of force on it. 192 newtons. Ooh, how much would it stretch? How about 1 meter, right? To pull up 1 meter would require 192 newtons of force. 192 newtons per meter. You guys get it? Okay. All right. So I'm on your desks. I know there's a green spring. There's a blue spring. Now I have the brown one, and I told you guys already the brown one is 192 newton per meter, right? I know the blue and the green are less stiff, but what's more stiff? Well, I know that there's a red one. I know there's a white one. I know there's a gold one. Okay. And I forget exactly what the rankings of these are, but I do know that these two are less stiff than the brown one. These three are more stiff than the blue one, okay, or the brown one. Okay. But let's get at least a couple of these before we switch over and do the Kahoot. And so you guys have those scales on your desk. I have an idea kind of what the number should be. But somebody tell me, what's one of the spring scales? What's one of the spring stiffnesses?
Blue is 2.
Blue.
2.5.
Okay.
I mean, blue
so,
is 2.5 meters. We're talking overall, blue would be 48.
that sounds about right. 48 newton per meter, right? Because you said it went up to 2.5 newtons, and I think it's the same 5.2 centimeters. So it'll be 5.2 over 100 meters, right? Okay, let's check that out. But it's 2.5 newtons on 5.2 centimeters divided by 100, convert to meters. Yeah, that is, in fact, 48 newton per meter. All right, so that covers the blue one. Check. Okay. So get at least one more on the board here. One more, you guys figured out. Okay. So you guys can read what the force reading is directly on the spring scale, how many newtons goes to. You guys got a ruler, so you can measure how far does it stretch to get to that point. Okay. So you know how much it stretches, how much force you put on it to get there. Okay. You guys are reading the side that says newtons, right? Not the side that says grams, the side that says newtons, right? Because newtons measures the force. Right. You divide those two, you get the spring constant. Okay. You gotta have one more before you flip over to Kahoot. Okay. Who's figured out any one of the other spring scales? Okay. Caleb got this one. Anybody else? Just divide this force in newtons by this stretch amount, right? In meters. Can you guys do that?
Gold would be 960.
That sounds reasonable. I could go with that number. 960 newton per meter.
96 times 2 is on to 90, so we'll multiply that by 10.
All right.
5 times the amount.
Yeah. I do know it's stiffer, so that looks believable. I could go with that. All right, so you guys get there? All right, let's we're about to flip over to Kahoot. Now, we're gonna do Newton's laws of motion. There's 20 conceptual questions. Some of them are, well, on each one of these laws of motion. So let's review these real fast. Newton's first law of motion, it's also called the law of inertia, right? This one says object at rest will stay at rest. An object that is already in motion will maintain its velocity. Velocity has two components to it: speed, but also direction motion, right? That will always be true until there's an outside force acting on the object. That's the only way for that to change, right? Right. Where did you want spacecraft? Classic example. It's just going. It's just going because of inertia. It doesn't have to have it. It's just going. No, it's just coasting through space. Newton's second law of motion relates forces and accelerations, right? Through mass. So what is the acceleration of an object? See, back in kinematic motion, we said we could describe acceleration by, distance, speed, time, like rate change of velocity. Okay? But now we're saying how you get acceleration. You get it by applying a net force to a mass, right? The more force, the more acceleration. The more mass, the less acceleration, right? Okay. And Newton's third law of motion says, well, forces always come in pairs. So if there's two objects like pushing or pulling on each other, there's always an equal and opposite force between these two objects. Okay. All right, you guys good there? All right. So with all that in mind, let's flip over to. Hold on. What's going on here? I think it's sharing the screen. All right. You guys got your phones up. All right, you guys ready to go? All right, so if you're still about to hop in, that 7-digit pin will show up at the bottom of the screen. Here we go. After a cannonball is fired into frictionless space, the amount of force required to keep it going. Zero newtons, right? There's just law of inertia right there. Right? That's the same as the Voyager 1 spacecraft question, right? What's keeping it going? Just inertia, right? So no force, 0 newtons. It's just going through space. Right. Math addiction, leading the pack. That's probably how you get there. Bryn, Alex, Casey and Bella, Mateo. If the force of gravity suddenly stopped acting on the planets. Yeah, you guys got that. Right, that is really good. All right, because actually this one would have worked better with the picture. So let me draw this out for you guys. Right. Suppose you have a star like the sun. You have you have a planet orbiting it. Here's the planet. Right. Let's say at some point the planet's like right here, right? Right. The planet's just going around. You guys see that, right? Right. And then suddenly you turn gravity on. Does that planet come around, make a 90-degree sharp turn and go this way? No. If I hold my ruler flush to the curve, it's just gonna keep going that way right there. Right? So turn gravity off, just keeps on going. Straight line. Constant velocity, right? Right. Hey, what about this? What if I change this problem up a little bit? Let's replace the planet with a ball. Let's replace the sun with your hand, and let's replace the gravity, force gravity, with like a tension force in a string. You guys see a ball on a string going, you're whipping around in a horizontal circle, right? And somebody comes along and cuts the string. Does that ball also make the exact same motion? Tangent to the path? Yeah, sure does. Law of inertia. There you go, right there. Right. Actually, that is a really good segue question to the next topic we're starting tomorrow. It's gonna be like centripetal force, orbits. All right, here we go. Math addiction, keeping the lead. 30 Newton force, 40 Newton force, opposite directions. What's the net force? Oh yeah, look at that. Yeah, so opposite directions, go subtract from each other. There you go, 10 Newtons. All right. Got Alex on fire. Got Mateo, Macy and Bella, Alex, Bryn, math addiction. Oh yeah. Equilibrium.
Oh, wait.
And probably should double the time on that one. Those are all true statements. So the net force on the object is 0, true. And the blue and the yellow are just saying in the horizontal and vertical directions, that's true along those components, along those axes, right? You could go 3 dimensions on the z-axis, that's also true. Now, guys, a few months from now, when we get to rotational dynamics, you guys know every time you open a door, there's like a force at a lever arm that's causing like a turning moment. Right? The physics term for that is called a torque. Later on, we're going to add the torque also has to go to 0 for equilibrium. All right. Oh, Bryn, taking the top spot. All right, so guy weighs 600 newtons. What is the tension? Each strand, you guys see 2 vertical strands of rope? See those 2 brown ropes? Now he weighs 600 newtons. What's the tension in each strand? Oh yeah, everybody getting it. Everybody getting it. All right, now I'm gonna flip over because I want to elaborate on this a little bit more. All right, so everybody got that one. That is awesome. All right, I'm gonna change this guy's weight from 600 newtons to just 100 newtons, make him a little tiny guy. All right, now, so guys, if he weighs 100 newtons, guys, everybody quick stare. This guy weighs 100 newtons. He's right in the middle. What's the tension in each strand? It's 50-50, right? 50-50, right? But I'm not going to put him right in the middle anymore. I'm going to put him over here. Suppose he's hanging out right here, right? And he weighs 100 newtons. 100 newtons. You guys see how he's like 3/4 way over to the right?
Yeah.
Right? Do you think the tensions to the rope are still 50 and 50? Ooh. What do you think this one is?
Like, says what?
75?
Yeah.
Say 75 newtons? What do you think this one is?
Like,
25 newtons? Right? Huh. Do you guys think if he's 75% over, that the one he's closer to carries 75% of the weight?
yeah.
It turns out that's true. Now, to prove that definitively, we actually need to talk about torque, which is going to come up a few months from now. So I'm just prepping you guys a little bit ahead of time. You know, I've got a little bit more about this story though. Suppose there's like some scaffolding. You guys see like pine painters walking around on scaffolding and it's held up by ropes. Looks a lot like this. Could be just like walking around on it, right? You guys know the guy Paul Hewitt showed demos sometimes. There was a time in his life he was working a bunch of oddball jobs in his 20s, and he didn't really know what he was doing in life. He was a boxer at one point. People punched him in the face. At one point, he was a sign painter. He was doing exactly this. He was walking around the scaffolding. He was walking with he had a friend who was also a painter with him. He was actually lived in Florida, and they would pluck these ropes as they were walking back and forth. Say, "Hey, walk closer to me. Walk further away." They were plucking these ropes, and hearing the tension change, and therefore the note frequency would change. Like, bing, bam, 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 right? Huh. I wonder what the relationship is between where we stand on the scaffolding and what's the tension in the ropes. And he was so curious by that question, he went back to college and learned physics. And yeah, that's why we have all these Paul Hewitt physics demos, because that question right there. Cool story. All right, back to Kahoot. Let's knock that one out of the park. Got Bryn keeping the lead. Friction is a force that always acts. Yeah, opposite of the motion, especially if we're talking about kinetic friction, right? It's always trying to slow things down. Opposite of the motion. Brenda's on fire. Alex in second. Mateo moving up. Which has more mass? A kilogram of feathers or a kilogram of iron? More mass. Ah, same mass, same mass. Right. different densities, different volumes. Same inertia, right? Same inertia, same mass. Push on with the force, they'll accelerate the same. All right, 1 kilogram is 1 kilogram. Got Missy and Bella, math addiction, Mateo, Alex, Bren in the lead. 3 kilogram bag of bolts. How much does it weigh in newtons? 3 kilograms weighs. Yeah, about 30 newtons, right? You guys know to go from mass to weight in the metric system, it's really easy. You just multiply by 10 meters per second squared, right? As long as you're surface of Earth, right? Yeah, 3 times 10 is 30 newtons. All right. Let's use 9.8 meters per second squared. It's a little bit short of 30 newtons. Go. Oh, math addiction, moving back to the lead. Acceleration produced by a net force. Yeah, all those statements are true. That is Newton's second law of motion. Directly proportional to the net force. So if you triple the net force, you triple the acceleration. Inversely proportional to the mass. Triple the mass, you get a third of the acceleration. And the acceleration is also in the same direction as the net force. Yeah, those are all true statements. Alexa's on fire. We got Macy and Bella in top 5. Bryn, Alex, but math addiction in the lead. When an object reaches terminal velocity, you guys need air drag for terminal velocity, right? What is its acceleration? Yeah, 0 meters per second squared. Right. Now remember, you can't have this in a vacuum, but if you have air drag in a very tall cliff, drop a ball off a very tall cliff in the air, right? Ball picks up speed faster, the air drag picks up. At some point, the air drag cancels off the weight of the ball. That's constant velocity all the way down, called terminal velocity. 0 acceleration. All right. Math addiction, keep the lead. A shuffle in the top 5. Bowling ball weighs 20 newtons. When held at rest in your hands, what is the net force? Yeah, 0 newtons. As anything that's just hanging out at rest, that's a type of equilibrium, and anything that's equilibrium is 0 net force, right? So holding bowling ball at rest in your hands, got 20 newtons down, 20 newtons up from your hands. Cancels out. 0 net force. All right, I tell you, hopping back in the top 5. Math addiction, keep the lead. Apple weighs 1 newton. The force of the apple when it is in free fall. Yeah, is 1 newton, right? So it weighs 1 newton. So if it's in free fall, it'll be 1 newton. Right? Now you know what? If you tweak the question a little bit, you could maybe make a case for the other ones. For example, what if you put air drag in there and it's a really tall cliff and the apple reaches terminal velocity? In that case, the net force is what?
0.
Yeah, 0 if it's terminal velocity, right? Okay,
But
but
the 9.8 was actually meters a second squared. Acceleration.
right, the apple's accelerating
Second squared.
9.8 meters per second squared. Yeah. How about this?
What?
What if the apple had a mass of 1 kilogram? What would its weight be?
9.8.
9.8 newtons in that case, right? All right, but they told you the weight here. All right, so a couple of you guys got that. Oh, math addiction got that. Oh yeah, got Bryn, Macy, and Bella, Alexis, Mateo. Whirlpool, 6 kilogram wagon with 18 newtons of force. What's the acceleration? 18 newtons, 6 kilograms. Yeah, 3 meters per second squared. So that's Newton's second law of motion, right? 18 newtons acting on 6 kilograms. Suppose she pulls horizontally and friction is negligible. Yeah, 3 meters per second squared. All right. Math addiction on fire. Pressure. Yeah, force per unit area. we talked about pressure in a few different contexts with a few different units. Guys, what is one unit for pressure? PSI? And what does PSI stand for?
Pressure per square inch. Pounds
Yeah.
per square inch.
There you go, pounds per square inch, which is like a force per unit area, right? Pounds per square inch to describe pressure, right?
Another one I don't know if it's exactly is G's, which is 9.8 newtons. Real value.
Okay, yeah, it kind of, yeah, so Newton per square meter, that's another one, right? Newton per square meter, which is also called 1 Pascal, 1 Pascal. Yeah, 1 Pascal is 1 Newton per square meter. You guys remember how many pascals of air pressure we have on us right now? About 100,000, so a little over 100,000. Okay. Yeah, okay, so there you go. Math addiction, the lead. You're on a frozen pond. The ice starts to crack. You lie down and begin to crawl. Why?
Obviously, right.
Yeah, decrease the pressure on the ice. See, you can't really change the force because the force is just your own weight. So can't do much about that. But you can spread out that force, right? Distribute the force. You guys ever heard of snowshoes? Snowshoes? Right? Suppose you're up in Alaska. There's like 5 feet of snow on the ground. You want to walk across the snow without sinking into it? You can take your weight and distribute it over a larger area, thereby decreasing the pressure. I think I showed you guys a bed of nails at one point. All right. We got here. Oh, you guys can read that, right? All right, so 17 newtons is the weight of the object, 9 newtons of air drag. The difference is 8 newtons, right? 17 minus 9 is 8. All right. I've got a different question for you guys. What is the acceleration of the object at that moment? Well, let's do sort of the shortcut way first, and then we'll go back and do like a proper way. Here's the shortcut way. You guys see how the air drag is about half of the weight of the object? About half. Do you guys think that the acceleration is about half of free fall? Right? Now that's kind of a shortcut. Let's do it like a proper way though. Now the proper way is you need a net. Guys, focus here. How do you get acceleration? Isn't it force acting on a mass? Right? Net force, 8 newtons. What is the mass of that object? What's the mass? 1.7 kilograms. You guys see 1.7 kilograms? Right? Now what is 8 newtons? Here. 8 newtons acting on 1.7 kilograms. That is 4.7 meters per second squared. That is approximately half of Earth gravity, isn't it? Oh, okay. So something about there, right? All right. Bat imparts a force on a ball. What is the reaction force? Bat hits the ball.
Diamond.
Ball hits the bat, right? So bat hits the ball hits the bat. Is that a action reaction pair? Okay. Now, guys, here, I've got my own question for guys. Which force is bigger? Ball hitting the bat or the bat hitting the ball? Same force? Same force? Yeah. Can't trick you guys. Same force, right?
Random example. You try pulling these things, making them hit the ground at the same time, and then what happens? This is always it out.
Unfortunate bug splatters against windshield of a moving car. Compared to the force of the car on the bug, the force of the bug and the force of the bug on the car, which force is bigger? Same force. That's straight up Newton's third law of motion, right? We got 2 different objects, the car and the bug. There's a force interaction between them. It's the same force. Opposite directions, but same force. Okay. Follow-up question. Same scenario, but compared to the change in motion of the car, the change in motion of the bug. The forces are the same. Masses are different. Ah, yeah. So the change of motion of the bug is crazy big, right? Right. Like when the bug and the car go splat against each other, right? The car barely changes its motion at all, right? Maybe it slows down a tiny bit, but hardly anything at all, right? Now maybe the change of motion of the car might be more significant if it's like a billion bugs, but right, it's going through like Bug City. But if it's just like one bug, yes, change of motion of the car, but change of motion of the bug, right? That bug changes motion like bonkers. It accelerates like crazy during that collision, right? Right. So same force, different masses, different accelerations. But kicks back to Newton's second law of motion, right? Last question. 2 people pull on a rope, tug of war. Each person pulls with 600 newtons of force. What is the tension in the rope? Everybody's pulling with 600 newtons of force. What's the tension in the rope? Ah, 600 newtons. There you go. 600 newtons. Couple winners. All right, to the podium with the bronze and the Macy and Bella. With the silver, Burn in the gold with 18 out of 20. Math addiction. And Alexis and Mateo, runners up. All right, nice job, guys. Nice job. There's all right, back over here. Let's do a review question, and then here's how we'll finish class. We're gonna do a review question here, then I'm gonna flip back over and we'll finish with some videos. All right, review question. Let's do a classic Atwood. Throw on a couple of masses here. All right. Let's say this mass is like 19 kilograms, just pick up something crazy. And let's call this mass how about 3 kilograms? There we go, 19 versus 3, right? And I got a couple of questions. One question is, what is the downward acceleration of the larger mass? Right? And the follow-up question is going to be, what is the tension in the string? We're going to do our usual assumptions for this Atwood, massless, frictionless pulley, the whole deal, right? Right. Something too is, suppose you guys take physics in college, they might approach this problem a little bit differently than I do. They might actually answer these questions in reverse order than I do, but I'm just going to do this the way I've been doing it all along. Right, take you guys through this review here. All right, so let's get some forces, free body diagram, get some forces going on. Okay. Well, guys, what's one force on this guy? How about a weight, right? Weight straight down. What's the weight equal to? How many newtons of force? Approximately. You guys say 198 newtons? Thank you. How about this guy right here? That little tiny 30 newtons, right? It's got 30 newtons versus 190 newtons, right? All right, so downward acceleration of mass B. Now, again, different ways to approach this. I'm going to do this from a whole systems point of view, a macro point of view, which is I see a tug of war, clockwise, counterclockwise. All right, guys see those fighting against each other? Okay, guys follow along because you guys know there's a quick question like this one. Okay. So, acceleration from a systems point of view, isn't that the net force acting on the total mass? That's just Newton's second law of motion, right? That's where accelerations come from. Okay. Guys, what is the net force from a systems point of view? What is the net force? Oh, yeah, you guys see 160 newtons, right? Right, so acceleration is 190 newtons minus 30 newtons. Acting on how much inertia? You guys see 19 plus 3 kilograms? You guys see that, right? Right. So there's 160 newtons acting on 22 kilograms. Oh, before I hit enter, I meant to ask you guys before I even started this process. Right here. Do you guys think the acceleration is closer to 0 or closer to pure free fall? What do you think it's closer to? Because remember the two boundary conditions. If these masses and the weights were the same, it would be 0 acceleration, right? It would just hang out there. And the other extreme is you could put all the mass all the way to one side and just leave an empty string on the other side. It'd be like pure free fall, 10 meters per second squared, right? What do you think this one's closer to? 0 or 10 meters per second squared? It's got to be closer to what? I'm thinking closer to free fall, right? Because like almost all the way on one side, 19 versus 3 kilograms, right? So I think when I hit enter, I'm going to guess maybe like 7 meters per second squared. Right? That's my guess. I don't know. I haven't tried it. Let's see. Hey, 7.27 meters per second squared. Right. That does look pretty reasonable, right? You guys got that? Right. How about follow-up question? What's the tension in the string? Now, to get the tension in the string, I need to go back and, well, label the forces, right? There's actually more force on these blocks. I think there's an upward tension here, F sub T, and there's the exact same upward tension here. And remember how tension is, it's an internal force. I hadn't considered it up to this point that I want to solve for it, right? It's also like the Goldilocks force. See how it's smaller than the large weight, but it's larger than the small weight? So it can drive the small one up and let the big one fall down, right? Right, you guys get it? Right. And now to solve for the tension of the string, I need to hone in on either block. Now coin flip. Let's say this one. So you could do either way. So let's go. No, I'm gonna break out new paper here. New paper so you can see that picture. Let's do a separate net force equals mass times acceleration just for the little block, little MA. Okay. Now net force, guys, is that the difference between these two? Is that net force, the tension force up minus the 30 newtons down? That would be the net force, right? True? Right. That's equal to the mass of this block, which is 3 kilograms. Accelerating upward at how much? How much is it accelerating upward? 7 meters per second squared, right? Right? Put that right here. 7.27 meters per second squared. Not true? Right. All right. Multiply these two together, add 30 newtons over. What is 3 times 7.27 plus 30? I'm getting the tension force is 51.8 newtons. There we go. All right. Is that really the Goldilocks force? Let's check. Because about 52 newtons, right? 52 is greater than 30, so this one can accelerate up. 52 is less than 190, so this one can accelerate down. Right? Actually, let's check our answer. Let's go to this block over here and see, does this really work? If this force is truly 51.8 newtons, right? Let's check this. So the net force on this block is 190 down minus 51.8 newtons up. That's the net force, right? And then, see if I divide by the mass, 19 kilograms, take this net force acting on this mass, shouldn't that tell me the downward acceleration of this block? Right. So let's take 138.2 Newton net force, these two subtracted, divided by 19 kilograms, and just focus on this single block. Right. Now I know what the answer on my screen has to be before I ever hit enter. Guys, what's the answer on my screen before I hit enter? There's only one number that can pop up right here. What's that number? Does anybody know the downward acceleration of this block? Did we already solve it? Right? We solved it from a systems point of view, right? We solved this a different way, right? It's like different paths through the forest, right? The number on my screen has to be this number right here. Right, maybe rounded a little bit, but let's see. Yeah, 7.7. Look at that. This is the same number, right? From a different point of view. Right, you guys got that? Right, are we good? All right, let's flip back over and finish with some video demos. All right, let's go. Get this guy right here.
But this is going to be really tough to see. So how are we going to actually determine what the right answer is?
If I were to drop it now, it would happen so fast you wouldn't really see clearly what's happening. So I've brought along my slow motion camera and you'll see it at 300 frames per second. And it's quite spectacular.
Well, that's ultra slow-mo. So that's exactly what we need to sort out this problem.
We'll give a countdown because it happens really fast.
All right.
3, 2, 1, drop.
Wow, did you see that?
I didn't really see which happened first. No, I need to slow that down.
Well, let's go to a slow motion replay and see what actually happened. So from the slow motion camera, we can clearly see that the bottom end stayed completely stationary even after you let go of the top. It waited until the whole slinky had collapsed down to the bottom before it itself moved downwards. How do we explain that?
Well, there are a number of explanations, but the simplest explanation is that the bottom end is sitting there minding its own business with gravity pulling it down and tension pulling it up, equal and opposite forces, no motion at the bottom end until the bottom end gets the information that the tension has changed. And it takes time for that information to propagate down through the slinky to reach the bottom end. So it's propagating down as a compressional wave.
And we saw that compression wave travel down, and it has to reach the bottom before the bottom even knows that you've let go at the top.
Correct.
And
could you hold this rock? We're going to have a tug of war here. Okay, Helen's going to pull the rope that way, and I'm going to pull it this way. Now, who's bigger, me or Helen? Yeah. Okay. Okay. Now we pull. Okay. Now, who's pulling harder? Am I pulling her harder, or is she pulling me harder? How are we pulling, gang? Check the neighbor on that one. What do you suppose? Is she pulling me harder, or am I pulling her harder? Huh? Who's pulling harder? Is that so? You used to say, I'm pulling harder because you see the rope moving this way. That's what you used to say. Remember the old days? When you didn't have that spark called what? Begin with an F. Physics, all right? And now you're getting that spark, right? And now you're starting to see the world a little differently. Let's try this with a couple of scales. Attach this right on here. Okay, now you pull that side and we can measure the force, gang, yeah? And I'll pull over here. Now you look to see who pulls harder, me on Helen or Helen on me. And here we go. How do the readings look, gang? Huh? Which one's harder? How about there? How about there? And what are they, gang? SS. Same. And you fire a rifle. Here's the bullet. Bullet races out. And the bullet has a force acting. But that gun kicks back. How much force? Really the same? The same. The same force acting back. Now, the acceleration of the bullet, a lot or a little? Answer begins with an L. A lot. Because here's the mass of the bullet. Here's the mass of the rifle. So here's the acceleration of the bullet. Boom! But here's the acceleration of the rifle. So the rifle only goes back to here. In the same time, the bullet goes from here to here. That bullet is accelerating like bonkers, huh? Inside the barrel. Now, when it gets outside, is it still accelerating? No.
All right.
No.
Yes,
It coasts.
great Tuesday
We talked
afternoon.
about this
See you
before.
Wednesday.
It's accelerating down.
Topic.
Why it drops. It follows the curved path.